gradient descent, but this time with a linear algebra background. Start with our basic problem. Maximize linear function over a constraint set. Graph what we're doing. And do gradient descent. Start at the origin. Calculate partial derivatives. I'll name the unit vectors unit 1 and unit 2 at every vertex. Move on to the next vertex. Directional derivatives exiting the corner. U2 is not unit length, so to take the directional derivative I need to scale. Continuing around all the vertices in the constraint set. Not unit length, so I need to scale. All we're interested in is whether the partial derivative is positive or negative, so the scale isn't relevant for the method. All we care about's the sign. There's our maximum. Both partial derivatives are negative. Gradient descent, move in the positive direction, or move in the positive direction. Now let's put some linear algebra in. Instead of having inequalities, I'll put in a variable to make them equalities. These are called slack variables. There's my vertices. Solving 2 equations, 4 unknowns. S1 equals 0 and S2 equals 0 are those lines. X equals 0 vertical, Y equals 0 horizontal lines. So my boundaries are zeros for my variables. And at every vertex, I'm picking 2 variables to solve for. So I have 2 non-zero variables and 2 free variables. And the free variables are 0 at the vertices. I plug in the function value at all the vertices. And the maximum's at the place we saw. But now for linear algebra, we have 2 equations and 4 unknowns. And we're picking 2 variables to solve for, giving us 2 free variables. So at the origin, let's look at the pair of equations. I'm solving for S1 and S2. X and Y are my free variables. Geometrically then, at my vertex, x is positive, x is negative, the vertical line x is 0. Y is positive, y is negative, horizontal line is 0. So my constraint set is where both are positive. These are called feasible solutions to the system of equations, where your free variables are positive. And I can go vertex by vertex and see that it has the same structure. Here I'm solving for x and s2. Y and s1 are my free variables. Y is positive, y equals 0 is the horizontal line, y is negative. S1 is 0, the diagonal line, positive and negative. And my feasible solutions are where everything's positive. And my corner is where they're both 0. I'm solving for x and y. S1 and S2 are my free variables. Same structure. So for solving a system of equations, there's our new problem. The corners that are outside have a negative solutions. These solutions are called not feasible or infeasible. Looking closer at the linear algebra, the free variable is becoming one I'm solving for, and the variable I solve for is becoming free. So the free variable enters the solution set, and the solution variable leaves the solution set. At the origin, I had two free variables, so there was two choices for which variable will enter the solution set and which variable will leave the solution set. And then we just repeat as we go. How we do this exactly is the simplex method.